Today we are going to discuss about moment of inertia. If a body is rotating about a fixed axis, then the linear velocity of the body is given by linear velocity is Vi is equal to Ri omega. So from this equation, the kinetic energy of motion of this particle is, usually the equation for kinetic energy is half mv square, but in this case the kinetic energy is given as Ki is equal to half into mi Vi square. So instead of this Vi square, we can substitute the value of linear velocity Vi. So we will get half mi Ri square omega square, where mi is the mass of the particle and the total kinetic energy of the body is given by the sum of the kinetic energies of the individual particles. Therefore, the total kinetic energy K can be written as the sum of the particles from 1 to n. So instead of this Ki, we can substitute this value of Ki. Since half is constant, we can take it outside and we can write the remaining terms. Summations I is equal to 1 to n mi Ri square omega square. Here n is the number of particles in the body. Since the omega is same for all particles, so we can take omega as constant, we can take it outside. So half into omega square, and we can write the remaining terms. Summation I is equal to 1 to n mi Ri square. So this new parameter is called the moment of inertia I. So we can write this equation as the value of I is summation I is equal to 1 to n mi Ri square. So from this definition, we can write the value of total kinetic energy is half into I omega square. So this value of I is independent of the magnitude of angular velocity. Independent of magnitude of angular velocity. So if we are comparing this equation with the kinetic energy, which is K is equal to half mv square, we can find that both the values, this I and m. The moment of inertia plays a similar role as mass does in linear motion. Next we are going to consider two cases. In first case, we are going to consider a thin ring of radius r and its mass is capital M. And it's rotating in its own plane around its center with the angular velocity omega. So it is rotating within the same plane. Then the kinetic energy can be given as half into mv square, where the mass is capital M and velocity v square, Instead of this velocity, we can substitute the angular velocity, which is the radius is r square, distance is r square, into the angular velocity is omega. We will get omega square. So the value of moment of inertia I here will be capital mr square. In next case, we are going to take a rigid rod of negligible mass of length L. The total length of this rod is L, with a pair of small masses. It's having a pair of small masses rotating about an axis through the center of mass perpendicular to rod. The center of mass is perpendicular to the rod and it is rotating like this. Each mass m by 2 is at a distance L by 2. So each mass is m by 2 and the distance between the masses from the center of mass is L by 2. Then the moment of inertia of the masses is given by, so moment of inertia of masses is given by so we know that I is equal to mass into the square of the radius, which is moment of inertia. Here mass is m by 2 and the radius is L by 2 the whole square, and another one pair is also there, so m by 2 into L by 2 the whole square. Thus for the pair of masses rotating above the axis through the center of mass perpendicular to the rod, so we will get the total moment of inertia I will be equal to ml square divided by 4.